Recording is rolling. It is Thursday, April 25th, and we're going to start a quantum mechanics journal. So I had you guys put these together yesterday, gave you guys this page of topics. And remember, we're doing, you guys wrote quantum mechanics journal, you guys wrote your name, and then I got about a quadrant of paper to keep notes on each one of these topics. I'll help you guys just going along, and there's going to be a guided story about quantum mechanics. So we're going to do the first 8 topics today, and then do a little bit each day for next few days. All right, so first topic is going to be how small is an atom? Because in quantum mechanics, well quantum is like quantized, like quantity, right? We're looking at increments of something, right? As opposed to something that's maybe a continuous, maybe something like that, right? And this is going to apply to physics that's really small. Like if you get smaller and smaller and smaller, right? Like let's say you start with, say, a meter stick and you divide that in half, right? And then you divide that in half, right? Now it's kind of close to this length, right? And you divide that in half, and then that in half. You can keep dividing half, right? Now, mathematically, theoretically, you could just keep dividing in half forever, right? And then mathematically, there's some number that exists, right? But in physics, when you get small enough, when you get to like atomic size and subatomic size, there is sort of like a theoretical smallest size that makes sense to talk about, right? Like weirdly enough, right? Or kind of spoil this sort, maybe I don't know, spoil, but I'll jump ahead a little bit, right? There's something called Planck length, right? It's like there's the smallest size you get to where it doesn't really make sense to subdivide in half anymore, right? Almost like the universe is sort of pixelated, right? Like look at any screen, phone screen, computer screen, and it looks like a continuous fluid picture, motion, whatever, right? But if you zoom down really small, really it's just pixels turning on and off, right? Some pixel, some space for light, right? Is the universe kind of like that? Well, if you get to quantum mechanics, yeah, kind of in a way. And the same thing is true for time. You can subdivide like half of a second, a quarter of a second, eighth of a second, right? But there's some time where it's like the smallest, it doesn't really make sense to like subdivide it anymore. Okay, so there's some other ones coming up here. Okay, so we're gonna say what happens when you get, what's the physics of really small thing? Now, the physics of again, we're like order magnitude of say like an atom and smaller. The physics gets really weird. It's different from classical mechanics, different from like anything else you guys have learned in this class so far. Okay. Right, so I think how small is an atom is a good starting point because you get a sense of scale where this physics starts to take place. Ooh, all right. So bring us back over here. Right. So here's oh, whoops, and switch this. All right. Here's some things I got. Hope you guys just go along. Out of that kind of interesting, right? How small are we talking about? Right. You're saying the number of nitrogen atoms that might take to fill a grapefruit. You think that'd be like the number of blueberries it would take to fill the entire. Woo. Okay, so maybe that's an idea of sense of scale. Right. Now, what about the structure of the atom itself? Right, is mostly empty space, and almost all the masses in the proton and neutron, they're in the nucleus. Right, and then a lot of empty space, and there's a little bit of mass in the electrons. Right, so that the density of the nucleus is like if you took 6 billion cars, which is like almost one per person for the entire Earth, and shoved it into 1 cubic foot box. That's the density that we're talking about. Right. While you guys are writing some stuff down there, by the way, how do we even know that? Like, you might take it for granted at this point that, oh, okay, well, I've learned that either like elementary or middle school. What is the structure of an atom? Oh, it's got this dense positive nucleus and it's got all these electrons going around it. Like, where did that model come from? Right? Like, model that, something that looks kind of like this, maybe, or some kind of atom, right? Is one of the early experiments was this guy named Ernest Rutherford. Maybe you guys learned this in chemistry. So back at, what's his 19th century, I think. There was this hypothesis like, okay, well, maybe there's protons and electrons because we know electric current and the whole deal, right? But maybe there's this plum pudding model they had where maybe they're all just kind of like jumbled together, right? And he said, I'm going to kind of probe this idea. So I think the experiment goes to like this gold foil and he's firing like alpha particles at it. And to his surprise, most of the particles just pass straight through the foil. It's like, wait, why did it do that? But every once in a while, a particle would like violently bounce off in a completely different direction, maybe like back towards how it was fired or off at some weird angle. Right? And that was some of the first experimental evidence for the structure of an atom. That you have, like a dense nucleus surrounded by lots of empty space and maybe like some electrons, something like that. That's how we know that. Right. So there you go. So that's the scale that we're talking about, and that's gonna kind of kickstart the story. Oh, what I meant to mention too is that the posters that are hanging around my room, like which are these thumbnail notes right here, most of these are going to be somewhere in this journal. There's not an exact match, but it's pretty close correlation. Right? You guys do have this page. If you guys remember a few weeks ago, we did relativity, theory of relativity. Right. So if you still have this page with these thumbnail notes, if you don't, I got some extra copies up here. Right. If you flip this page over, you get all the quantum posters. Right. So you guys got those. Right. Again, a lot of these show up in this this journal we're putting together. All right. So this is a good start point. We're talking about crazy small. Okay. Right, now go back to about the end of the 19th century, and I'm going to bring in a weird part of the story that I have a poster for, but I didn't actually put it in the journal, so it's a little bit extra outside the journal. Right? Is something happened? It's called the ultraviolet catastrophe. Sometimes it's called, right? And it has to do with waves versus particles and what is what. So they were thinking back to the 19th century. They thought they had a lot of physics figured out, and that matter could essentially fit into one of two categories, one of two baskets, right? Either it's a particle or it's a wave, right? Now, what's a particle? Okay, something that has like a definite mass and location and speed and possibly acceleration, something like that, right? what's a wave? Okay, something that has a wavelength and a frequency. And something can be categorized as one or the other, but not both. It fits into one basket or the other. That's the thought going back to the 19th century. Right? Now, then they were looking at electromagnetic waves. So it would be visible. Right? Here's the visible spectrum. Here's infrared. Here's ultraviolet. Right? And say, okay, well, what would classical theory then predict if we say like crank up the amplitude, like crank up the temperature, right? Suppose it was like 5,000 Kelvin. Right? Now, here's this black curve is classical theory, like 5,000 Kelvin. What would the spectral radiance be expected to be? Now on this graph, I cut out the vertical numbers, but there could be numbers you could only match that graph. Okay? And classical theory says, well, if you crank up the temperature of some wave to like 5,000 Kelvin, then even in the visible spectrum, you guys see this curve like goes like off the page, right? It'd be like it's so crazy out. So physicists were working with ovens, right? And they cranked up the oven to 5,000 Kelvin. They said, ooh, well, according to classical theory, if we open the oven door, it should effectively like blow our face off, right? So they did that experiment, and face is still intact. What's the deal? Right? Why is the observation not following the theory? Here's the actual observation: is this blue curve here for 5,000 Kelvin, right? It peaked at some value that wasn't off the page, right? Didn't blow their face off, right? And then here's some like cooler elements, 4,000 Kelvin, 3,000 Kelvin, right? But the observation was not matching the theory. So so they filed that away. They said maybe there's something in physics we're not quite getting at, right? Right. Then not too much later, along comes Heinrich Hertz in 1887 and does this experiment that leads to something called photoelectric effect. It goes like this, right? Now this is a quadrant on your journal, right? So this graph right here. So kinetic energy versus frequency, right? And okay, so you guys see that straight line right there, right? Here, I'll help you guys out with this too. I noticed that it didn't catch us until recently. I think I've reordered these topics over the years, and somehow I printed out the wrong version of this. We're going to do number 4 next. You guys see number 4, photoelectric effect? It's really the next part of the story. Right? So here's what was happening was, suppose you have a photovoltaic cell, like a solar panel, right? Now they had not exactly. It was a little bit different rig. I'll show you guys a short video here in a minute, but think, kind of approximately that, like the equivalent of that, right? You shine some light on it. Now, what if you're getting no energy on the solar cell, right? Like if you shine a light on it, you should be able to get energy and maybe like charge a battery or something with your solar panel, right? But maybe you shine a red light or something with a low frequency, high wavelength, and you're not getting any energy. Well, in classical theory, you might just say, hey, what if I just turn up the intensity? What if I made the light like 2 times as bright? Now it's a super bright red light. Okay, well, that's got to do something, right? And they were still getting nothing. It's like, okay, this is weird, right? This doesn't really match up with like classical theory of what waves should do. Right? And oh, by the way, we think light is a wave. We've got it pretty well established. Why do we think light is a wave? Because of something called double slit experiment, an early version of that. If you take a card, cut 2 slits in it, shine a light through, you get an interference pattern on the other side. That only happens with waves. Hence they thought they had pretty well established by the end of the 19th century. Well, light must be a wave, right? Okay. But then what they did with this experiment, they tried something a little different. They said, hey, let's not change the intensity, let's change the frequency, right? Which is like wavelength and frequency are reciprocal or inversely related. Okay? So what if we go from like red to green to blue? That's not making it brighter. That's like changing the color. Okay? And then they did get effects. They noticed that past a certain threshold frequency, I got a threshold frequency labeled here. Okay? As they increase the frequency, that would also increase the energy that they would get out of that light. Okay? Now, putting energy in electron volts, you can put it in joules. That's okay too. Electron volt is a tiny amount of energy. I forget how many joules equivalent that is, but try and compress it. Okay? But the important part is this all lined up in a straight line relationship. I'll show you guys an actual graph of that later too, right? And you can describe this graph with an equation, like E energy equals the slope of this line ends up being something called Planck's constant, H Planck's constant times the frequency, and then for an intercept, I'll do minus psi for the intercept, something like that. Okay, and then below the threshold frequency, increasing intensity of the light did not increase the energy. Okay, so increasing make a more intense light laying on, say, like your solar panel, you could think, okay, gave you no more energy, but somehow turning up the frequency did. It's like, and it's that straight line relationship. So that's weird too. Right? What in physics have we seen like that before? In 1887, we haven't seen anything like that. So that sits around for almost 20 years before, in 1905, Einstein finally interprets this correctly, right? As light has not just wave-like properties, right, which we know light's a wave, right? But light also has particle-like properties. Right? What was his interpretation of this? Right? I'm about to give you guys an analogy with that too. Right? Right, so you guys get this down. Right? You guys got this graph? Right? So here's what let's go ahead number 2. You guys see E equals HF? I'm gonna say energy in quantized packets. Right. Give you guys this garden hose analogy. Suppose there's a couple of garden hoses. Right? So I got a hose and another hose. Right? And I'm gonna roll marbles down the hoses. Once I'm gonna roll at low frequency, it's frequency. Right? The other at high frequency. Right? Then I'm rolling marbles down. Now low frequency, maybe that's like 10 marbles per minute, just like marble, 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 right? And since this does have a connection to waves, maybe I'll draw it sort of like being like a wave, maybe something kind of like, okay. So it's just a few marbles per minute, maybe something like that, right? Now high frequency, maybe I'm rolling like a bunch of marbles, right? Like large number of marbles per minute, right? Again, just to kind of connect it back to the idea of being also having wave properties, I'll draw it kind of that way, maybe in some to the wave, right? But these marbles could represent like packets of energy. And to connect this back to electromagnetism, Einstein had a term for this, and he called it photons. Photons, right? So photons, these could be like packets of light energy, right? And this could explain the photoelectric effect, right? That light came in these particles called photons, right? So now light is both a wave and a particle. So like this question of what fundamentally is light? Is it a wave or particle? Went back hundreds of years, right? Interestingly enough, Isaac Newton had thought that light was made out of particles, right? And he called those particles corpuscles. Now, I don't know if he had any kind of experiment to back that up or why he thought that was the case, but he thought that, right? And then in the next couple hundred years, science had kind of settled on, okay, well, light must be a wave and only a wave. Then Einstein comes along and says, no, actually, Newton was kind of right all to begin with, right? Light is also particles. So now there's this duality, like light is both. Light is waves and light is also particles. Right? And light comes in these packets of energy that you can label photons, right? And here's why this explains this photoelectric effect. Because if you like double the frequency, that's like doubling the number of marbles per minute, right? That effectively also like doubles the energy and explains this direct relationship here. Okay, right, you guys get that? All right, let's do. Right, you guys good so far? Right. Let's flip back over here and fill in a little bit more details on the side. See what I got here. So I've got some data for photoelectric effect. Is that going to give it to me? No? All right, my computer's been all squirrely all day. Oh, we are getting it. Right. Now this experiment's from, this is data from 1916. The original version of this experiment was back in 1887, but you guys see energy per frequency, right? And all those points line up pretty well in a straight line right there. Oh, and there's your threshold frequency for this particular experiment. Okay, let's look at photoelectric effects. Oh, I forget if I mentioned this too, but yeah, did Einstein win the Nobel Prize in Physics? Yes, but not for relativity, which is what he's most known for. He actually won it for this interpretation. Right, so he goes on a little bit more, but you can see eventually he's leading to this graph that, hey, look, that looks just like a photoelectric effect, doesn't it? Right. All right, so something about like that. All right, so I'm gonna cut him off there. Let's bring this back over here. All right, fill this next bit right here. All right, so okay, so we did 1 and then 4 and then 2. Great. Set number 3 here. Right. So Planck's constant, that is actually the slope of this graph. See, it's labeled H. Right. So guys, during the next week, when you see the letter H, right, that's what Planck's constant is. All right, I'll tell you guys what this is. This is 6.626 times 10 to the negative 34. Wow. I think that's the smallest number that you guys have seen so far in this class, right? 10 to the negative 34, that's like 0.0000. It's just a string of zeros before you hit the 6626, right? And it says units because energy could be in joules, frequency could be in hertz, just like joules per hertz, right? And okay, hertz I remember is like 1/second. So joules per hertz, that's the same thing as joules seconds. So joules times seconds, right? Because it's the same thing as joules divided by hertz, right? It's the same thing, right? So like that, right? That is a fundamental constant of nature, kind of like the speed of light or the universal gravitation constant, right? Like nobody knows why any of these constants are what they are. They've just been observed to be these numbers, right? The slope of this graph has just been observed to be whatever it is, right? Nobody knows why, right? Also in this quadrant, I threw in some other terms that start with Planck. Right, so let's go Planck time. Planck time is, I'll play you guys a couple short videos on these too, right? Is 5.39 times 10 to the negative 44 seconds. Okay. By the way, there's more Planck time in a single second than there are seconds since the Big Bang of the universe. Okay. And then Planck length, we're talking about 1.616 times 10 to the negative 35 meters, right? Because these are extremely small numbers, right? This is like the universe quantized. So you've thought about the universe being kind of like a computer where there's like pixelated sort of, right? But yeah, there's the smallest unit of distance, there's the smallest unit of time that it even makes sense to talk about. These are like the pixels of the universe, right? By the way, if you divide this Planck length by this Planck time, that many meters per that many seconds, guess what number you get? Meters per second. Yep, it's a constant. How about the speed of light? Fundamental constant, right? You get the speed of light. That divided by that is the speed of light. Interesting connection too. Yeah. So there you go. There's those values. Let me queue up. Well, okay. Some of you guys are writing that. I'm gonna queue up the next. There we go. Ooh, all right. Crazy time there. All right, so moving on here. Great. So now at this point of the story, there's definitely some kind of duality for light, right? So at this point we've established, okay, we know light's a wave, but now Einstein's saying light's a particle too. That's this interpretation's photoelectric effect, right? Now we're gonna zoom ahead a little bit to a guy named de Broglie, uh, who I don't think he was actually a physicist, but he did practice like physics as a hobby, right? He started to look at, well, at the time, what was some new physics around, right? So particles have certain properties, waves have certain properties, right? Particles have things like momentum, momentum is mass times velocity. At the time, E equals mc squared, energy mass equivalence. That was new about 100 years ago, right? And then waves have properties like speed equals wavelength times frequency, right? Here's special speed of light, right? And you say, hey, I wonder if we can like combine these two ideas, these two properties, right? Like I know E equals mc squared, right? But now there's this new quantum mechanics coming up. There's this photoelectric effect, E equals hf, right? Planck's constant times frequency is right? Hey, I wonder if I can take this E, substitute in mc squared, take this hf and substitute in for frequency. What would frequency be? Is that speed divided by wavelength? Speed divided by wavelength, right? Now that could be true for light. Okay, that should work, right? Although photons are massless, so maybe that's an interesting implication too. So what do you even do with that, right? But what about not light? What about any other kind of particle, like electrons or something? I wonder if that follows this too. But see, that wouldn't be moving at the speed of light. That would be some different speed. So let me just replace some generic speed for C. I'll just put in some V, right? And then what you can do is solve for this wavelength. And you get the wavelength of a particle. Takes Planck's constant divided by the momentum of the particle. So there you go. Right, that is now the wavelength of a particle. Right. So we extended this wave particle duality to more than just light. You know, maybe like any particle, right? You know, Planck's constant, which is tiny, 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 it's 10 to the negative 34, divided by the momentum, right? That tells you the associated wavelength. Okay, great. What could that possibly be good for? Oh, by the way, I've also got a poster for that, so see the poster, I'll be out too. Right. What could that possibly explain? It does explain something. It explains, well, how about all of chemistry? Right, and I'll show you guys why. Right. So do you guys remember in chemistry? Here, we're moving on to number 6 here. You guys remember chemistry? Learning something about energy levels. I'll draw a diagram here. There are a couple of versions of this. Right. So one of them goes like this. If you do increasing energy, right. Did you guys learn in chemistry something about like orbital levels? Like there's a 1s level, there's a 2s, a 2p, a 3s, 3p, and a 3d, and then there's a 4s, and it goes on from there. Right? There's more to it than that. Right? But then you say, well, like, what order do electrons fill these orbital levels? Right? Each one of these can hold 2 electrons. So the 1s could cover both hydrogen and helium. Right? And then when you go to lithium, element number 3, right now you need to go up to the 2s level. Right? Then it goes 2p and 3s. Then it goes 3p followed by 4s, and then back to 3d, right? And then it goes on from there. Right? So that's not the entire chart. That's part of it. Right? Okay. So do you guys remember that model of an atom? It's like there's a positive nucleus, has the protons and neutrons, and then the electrons orbit that. Now, maybe that sounds kind of like a solar system, right? Like there's a star in the middle, and then all the planets go around, right? Which, okay, kind of, but then also kind of not, because there's these specific orbital levels. There's only certain levels that electrons can actually fill, right? And that's because of this wave particle duality. The fact that electrons actually have more wave properties than particle properties in some sense, right? Yeah, they have a mass and a velocity, but watch this, right? What if the electron had like these waves, right? Now the actual orbital waves look kind of crazy, so I'm gonna give you guys like a simplified 2D version, right? But there could be like some associated wavelengths to these, right? Kind of like if you're making a paperclip chain, and you could do 4 paper clips or 5 paper clips, but you couldn't do like 4.5 paper clips. Like that would make sense, right? So for an electron to like close in on itself and complete the orbit, right? There would be some integer number of wavelengths, something like that, right? In real life, there's like crazy 3D structures, but that kind of gets at the idea, right? Something like that, right? Oh, it's okay. So this sets up all of chemistry, right? Because why do any chemical reactions happen? Well, it's probably something to do with like valence electrons, like noble gases. Their outer shells are filled, so they don't want to react with anything, right? Lithium has one electron on the outer shell, so it crazy wants to react with everything, right? So, okay, and then like all chemical reactions, right? And then okay, so it looks like chemistry is founded on this type of physics, right? And then all biology is founded on all chemistry. So yeah, like these boxes right here could but yeah, there's like all of your high school science right there, right? In a nutshell. Right. So let me flip over, show Paul Hewitt saying the same thing more or less. Find Paul. Oh, and then here just to show you guys too. I think this file got corrupted or something. But well, you can kind of make out what's going on there. Actually, you know what? That is the same thing I drew you guys, but upside down. 1S, 2S, 2P, blah, blah, blah. Right. And a different version of the same thing is where's this other file? It's gonna give it to me. Give me that one. Aha, there it is, right? That's the same thing, just a different view of it. It's going up, go 1S, 2S, 2P, and so on, right? 4S before 3D, right? Right. But there's only like these discrete levels that electrons actually fill. They can't just fill anywhere, right? Like if this was planets going around the star, planets can kind of be any distance from a star, right? If they're closer, they'd be going faster. If they're further away, they'd be going orbiting a little bit slower, right? Kepler's third law, right? But electrons, no, there's like only certain orbitals that they have to be filling. So there you go. There's the foundation of all chemistry. And I want to focus on one specific version is why is glass transparent? Right? You guys ready for number 7? Why is glass transparent? Right? Why can we see through that window? Here's the connection straight to that idea. Why? All right, so here's a little bit more of it. You guys get the idea. All right, let's go over here and fill in these notes in. Okay, so why is glass transparent? Or guess anything is transparent, right? Like this plastic pen right here, you can kind of see through this a little bit. Right? Why do some materials the visible light goes through and other materials not? Right? So the quantum mechanics explanation, well, what you just said. Now, glass, the main constituent of glass is silicon dioxide. I guess it's more of a molecule than a single atom, but you guys get the idea, right? Silicon dioxide, that could be this, right? There's some kind of electrons somehow orbiting that molecule structure, right? And if you send a photon of light, then, well, for most opaque materials, like the walls of this room, it's going to bump up the electron, and hence the photon is absorbed, hence the photons do not travel through, and it's not transparent. But for glass, right, that energy gap is too much, right? So the energy gap is too large for photons of visible light to be absorbed. So the photons of visible light go ahead and pass through. That hence makes it transparent, right? And so we got like a train of thought here, right? So there's this photoelectric effect. Then Einstein says, "Oh, light has this dual nature of waves being both a wave and a particle." Then De Broglie says, "Hey, maybe we could extend that to other objects, maybe like electrons, right?" Then we got the foundation of chemistry, and here's one funny little corner of this is like, why is glass transparent? Now remember, that's only in the visible spectrum. Guys, does that glass window block infrared light? Yeah, if you could see in the infrared part of the spectrum, it actually would no longer be transparent. Same thing for UV. If you could see in UV, it blocks UV light, right? But the visible happens to go through, right? What about radio waves? I bet if you had a radio, turn it on, the radio waves could go through the ceiling, right? So different parts of the spectrum go through different materials, and the explanation is quantum, right? This quantum structure, this dual nature of wave particle duality for electrons, really, electron configuration. All right, now you guys ready for number 8, wave function and Schrodinger's equation. All right, so if you ask like, where is any particle located, like in classical physics or like in this class up until like last Friday, there'd be some definitive answer for that. Like one of the first experiments you guys ever did, one of the first labs you guys ever did was rolling Hot Wheel cars down inclines. And if you wanted to model an equation of like, where's the car going to be for some function of time, you could do that, right? Some did like x equals 1/2 at squared. You can predict, millisecond by millisecond, where's the car going to be? That's the location, right? Now, funny thing, when you get down to quantum level and you ask the same question for electrons, right? Let's say you're trying to figure out like, what do these electron orbitals look like, right? Is that electrons actually exist probabilistically. I put here particles exist probabilistically, right? And that, measurement causes the collapse of the wave function. I'll get to that in a minute, right? But say I have a probability versus location graph, right? This is one of the reasons that I introduced this whole quantum topic with a few days of statistics, right? Because if you understand statistics, this graph is about to make more sense. Now, I showed you guys over the last few days more simple normal distribution curves. Right? This isn't going to be exactly that. The Schrodinger equation tells you what the curve looks like. Here's probably a little bit closer to what it actually looks like. It looks something a bit more like this. Right? If you can graph Schrodinger's equation, right? You get a probability curve that looks something kind of like this. Right? So where is an electron going to be? If you set out to measure it, well, most likely it's going to be here. Maybe there's like a 40% chance it's going to be between those two bars, right? But maybe like a 20% here and 20% here, and maybe like 10% and 10%. Okay, so there's like percentage chance that you'll find it any particular location. Right? Now, funny thing is, when you make the measurement, that probability wave function actually collapses to just a single reality, and you actually do get a single answer. Maybe it's like between like these two bars. And then what happens is this whole thing collapses and reorganizes about that point. So now this peak kind of shifts over here, right? So you guys ever heard that adage, like if a tree falls in the forest, does it make a sound? Okay, so it just seems kind of crazy. Like in classical physics, of course it makes a sound. There's some kind of crash and collision going on, right? But in quantum mechanics, it's kind of an applicable question, because by observing, making a measurement, where is that electron? It can only show up in discrete locations, and this wave function collapses and it reestablishes itself. So the observer, in effect, affects reality. That's been an opposite of an assumption we made so far in this class. Like every single lab you've done, you assume that you can set a pendulum into motion or a Hot Wheels car down an incline. It's going to do whatever it's going to do. You built some model of the world, and now you can be an independent third-party observer. But in quantum, that's no longer the case. When you're observing, that actually has an effect on where the electron shows up. Okay, so that's our pause point today. We'll pick up that story tomorrow.